Problem 5 is probably the second most complicated problem on this test. Too hard to be on, or on this practice test. It's too hard of a problem to put on the actual test, but it is a good problem that illustrates a lot of key points about what we're doing in this chapter. So there's a ball rolling down a hill, and the ball has a center of mass that's offset from the center with some eccentricity epsilon. Now, one piece of information that's not given in the problem, and you do need to solve this problem, is the inertial mass of the ball. So whether this is even if there was no eccentricity, so if the center of mass was right in the center of the ball, the rolling motion would be changed depending on what the inertial mass is. So whether it was a hollow, just a shell, or whether it was a uniform solid, or if all the mass was concentrated at the center, would make a difference on this problem. So we need to guesstimate what the inertial mass is. So the inertial mass about that center point of rotation, we're just going to call that I. And then we're going to say the total kinetic energy is the translational energy of this object plus the rotational energy. And that's given by 1/2 mv squared plus 1/2 I theta dot squared. Now note v is now the velocity of this center of mass of the object, which is located here. So this is where it gets a little more tricky, because you have this mass that's moving not directly along with the center of the ball, but it's rotating about the center of that ball. So I chose to orient coordinates x and y to first find the velocities down the slope and perpendicular to the slope. That seemed natural to me. And then I defined this variable theta, which is the angle that this ball has rolled down the hill. Now that angle can go past 2 pi and it won't be back at its same spot. So you have to keep in mind that as this rolls down the hill, theta can go past 2 pi, it can go 4 pi, 8 pi, 100 pi, and that just means the ball is going to keep rolling down the hill for any, when you get back to multiples of 2 pi, this little center of mass point here is going to be oriented in the same position relative to the center of the ball, but the whole motion of the ball can continue down the slope. So yeah, theta is the rotation of this ball from its initial point there. And we can find the velocity in the x direction and the y direction separately. So the velocity of the center of mass here has two parts to it. It has two components, Vx and Vy, but if we look at just the Vx component first, the Vx component is made up of how fast this ball is moving, so the center, plus how fast this little point is moving relative to the center. So there's relative motion here. You've got the total mass moving like this, and then this point is moving relative to the center. Now, how fast the ball itself is moving is just given by big R theta dot. So this term here is how fast the center of that ball is moving. And this second term here is how fast the center of mass is moving relative to the center of the ball. So if you look at this motion here, the motion of this point relative to the center of the ball is in this direction right now, but the component of that in the x direction actually goes as sine theta. So if theta is 90 degrees, for example, if this was up here, then Vx would be in this direction, be directly in line with this little rotational motion about the center. So the x component of velocity has these two components. It's how fast the whole ball is moving, this first term, plus how fast that center of mass is moving relative to the center of the ball. The y component has that same motion relative to the center, but it does not have the motion perpendicular to the hill because the center of the ball is just traveling parallel to the hill. So you just get this term here. Now, fortunately, when you square them and add them together, some things nicely combine because you get sine squareds, thetas, plus cosquared theta terms. And you get this theta dot squared term is common to all of them. So you get this nice expression here. Now note the total kinetic energy is 1/2 m theta dot squared times all this in this bracket. This is the translational term, and this is the rotational term. Then the potential energy of the system is is dependent on how high that center of mass is. So not how high the center of the ball is, but how high the center of the mass is. And so that's given by two things. It's what the x position is of the center of the mass times sine of alpha. So if we look back here at the diagram here, as you move down this slope here, how far you go in the x direction. The component of that in the vertical direction is given by x times sine of this angle, which is alpha here. And because x goes downwards, there's a negative there for the potential energy here. The other component is how far the center of mass of that ball has moved in the y direction, which is, its component in the y direction, but then how much that lines up with the vertical is now, it's actually y times cos theta. So if you redrew this little triangle, cos alpha. This direction here is made up of this plus this. And if you kind of reorient how these triangles all work out, this little angle here is the same as alpha here. So the potential energy is going to be this negative mgx sine alpha plus mgy cos alpha. We found earlier that the x position is given by r theta minus r cos theta. Actually, we didn't find that. We found the velocity, so this is a little different. So if you look at this diagram here, the position in the x direction is the how far it's moved down the hill, which is r theta. So as this rolls down, the center moves the same distance as this arc length of this circle, which is r theta. And but if theta is 0, then this little r is pointing back that way. So that tells us that little r points kind of in a cos theta direction back up the hill. So the y or the x component of position has this this extra term here, r theta minus little r cos theta. And for the y term, we still have this mgy cos alpha, which is mg cos alpha times r sine theta. So that would be, as this ball rotates, if theta is pointing directly this way, it's totally in the y direction, and that's when theta is 90 degrees. So that tells you it goes as sine of theta. So the Lagrangian is a big mass, or I guess, I don't know if you want to say mass, but it is lengthy. You can factor out some things if you want. I didn't do that till later. I don't know why. But you take the derivative of the Lagrangian with respect to theta, and you get a nice big long term like this. You do it with respect to theta dot, and you get this long term. Now when you take the time derivative of that, you've got, so it's not so simple as we normally experience where we've got just theta dot time derivative. We've got derivative of this times this, which is this first part, plus the derivative of all this times this. So the derivative of all this, only this term matters, so you get a 2 big R little r m cos theta, and then times a theta dot, and then that multiplies with this other theta dot, so you get a theta dot squared. So you set this term equal to this term from the Euler-Lagrange equations, and if you write it all out, some things cancel, so one of these cancels with one of these. Divide through everything by little m big R squared, and use the fact that the ratio of little r over big R is this epsilon, and you get this nice little expression here that says the angular acceleration is g times all this in brackets divided by r times all this in brackets. So yeah, it doesn't look very nice. As a sanity check though, we can check, so if the center of mass was right in the center of the object, then epsilon would go to 0. So little r would go to 0, and the eccentricity of this would go to 0. So then we should get the usual result of a round object rolling down the hill. And so if we put in epsilon is 0, this term goes away, this term goes away, this term goes away, this term goes away, this term goes away. Simplifies nicely, you get this expression here. And if you multiply through by r, you get r theta double dot is g sine alpha over 1 plus I over mr squared, which is the regular result you would get for a ball rolling down a hill. If you think of this r theta dot as the acceleration in the x direction, then the acceleration in the x direction is g sine alpha, which is what you'd expect for something sliding down a hill. But if there's additional rotational inertia, it's kind of like an extra mass slowing it down here. So this extra term in the denominator. So everything checks out. So sanity check looks good. It also seems to make sense that if epsilon gets bigger, some of these terms get bigger. Excuse me. So the effective mass gets bigger down here in the denominator. So yeah, the acceleration is kind of like a force divided by a mass, and the mass gets kind of bigger if there's more eccentricity, because you have this center of mass is kind of rotating about the center and not sliding nicely along. There's some other terms here which is not real clear where they come from. It's yeah. So this would be how the object like rotates around. It's going to do this and this and this as it goes around, and that has to do with yeah. If you plotted the equation of motion of this with some numerical solver, you could see that motion happen. So it looks complicated, but it is a complicated problem. So if you tried to do this with Newton's equations, you probably couldn't even come up with a differential equation. Or if you did, it would be very, very hard to get to. So the Lagrangian works. Then you can give this to a computer, and a computer can plot the trajectory of what would happen to that ball as it rolls down the hill, and you're golden. So